So for this series here, we are told to evaluate it as n equals 1 to infinity. And does it converge or diverge? Basically, do the partial sums add up to be a finite number? Or do the sums go on for infinity or just do some weird crap in between, thus divergent? So what we're asked here is, okay, what kind of series do we have? That's the first question that we have to ask ourselves. I look at that there and I say, well, that's not a geometric series. That's not a harmonic series. Does kind of look like maybe we could do something with the telescopic series. And if you don't believe me, think about partial fractions. Do you remember doing that at all? I'll show you what it is. Maybe you did it during integrals. I would think that would be integration by partial fractions, when you have something over something, or a constant over a quadratic, or something in between like that. We can actually write this a little differently. If we have irreducible factors in the denominator, we can set up a partial fraction sum. So let's say that 3 over n plus 4 n plus 3 is equal to a over n plus 4 plus b n plus 3. Okay? We can actually set up like that. Notice I factored the denominator and I set them equal to partial fractions of each denominator. This is a true statement. So what we can do next is we can get like terms in the denominator, and to do this we are just going to multiply this one by n plus 3 because we want to get a common denominator among all of our terms that are separated from each other. So in this case, this is going to be a n plus 3 over n plus 4 n plus 3. This is going to be added to b n plus 4 n plus 4 n plus 3. This is going to be equal to 3 over n plus 4 n plus 3. So for each of you, multiply the top and bottom by something. And they could cancel, yes, but what I want you to notice here is that we have a common denominator for each. We're allowed to ignore it. And why is this so? Well, imagine multiplying this over, and it would cancel out that one and that one. So we're going to cancel out all of our denominators if we were to multiply by the common denominator on both sides. So this is going to be 3 is equal to a n plus 3 plus b n plus 4. So we're allowed to cheat this here to find what are the values of a. We don't need to use, what would it be, the systems of equation strategy. We can just cheat it. Okay, we're going to notice that a, if we plug in negative 3 as our n value, a is going to go to 0. B here is going to be negative 3 plus 4. So if I were to set this up before evaluating n equals negative 3, well, this is going to be just b is 3. Hopefully that makes sense to you. And then simply we could do, okay, negative 4. So if n equals negative 4, well then a is going to be negative 4 plus 3. That's a negative 1a. We just divide out the negative. We're going to see that a is really equal to negative 3. So hopefully you remember the cheating method from the integral section of this course. But it's going to be negative 3 over 3. Alrighty, so I'm going to go ahead and erase all this. Now that we have an equivalent expression, we are allowed to just say, okay, I want to take the series of this. Now this definitely looks like a telescopic series. Remember, the telescopic series says, okay, if you have a fraction plus or minus another fraction, you're allowed to take the telescopic series of that. And we'll see a nice little pattern emerge. I'm going to quickly rewrite this where I'm going to flip-flop each. So I'm going to say that 3 minus 3 n plus 4 n plus 3. So I just kind of swapped their positions and brought out the negative to make it nice and dandy for us. So let's evaluate this. Remember, for this we need to first identify what's happening at 1 to some finite number like 3. So n equals 1, our first term, n equals 2, n equals 3. Then what's happening at infinity, and then working our way back? Do terms cancel out? That's the characteristic of a telescopic series. So let's evaluate this at 1, n equals 1, n equals 2, and n equals 3, and let's see what we get. So plug in 1 here, we're going to get 3 over 4 minus, and then we plug in 1 here, we're going to get 3 over 5. All right, hopefully this idea makes sense. All we did is evaluated these partial fractions, or these partial sums, at n equals 1. Now at n equals 2, it's going to be 3 over 5 minus, this is going to be, at 2, this is going to be 3 over 6. Alrighty, so notice we have some terms canceling, like that. And then at n equals 3, we're going to have, let's see, 3 over 6 minus 3 over 7. So we can imagine that our denominator every time is kind of growing by 1. I hope you see that pattern. It's just going to cancel out every successive term except for this term here. So our sequence are, because these are just a sequence of sums that we're asked to. What is the overall sum of all terms? Well, we're listing out each partial sum, and we're noticing that terms are canceling out except for this first one. So this is going to be this plus some other factor, which we're going to see we have at infinity. Alrighty, so hopefully that idea makes sense. That it just keeps canceling out. Now let's look at infinity. Let's say 2 before infinity, 1 before infinity, and then at infinity. And I should rewrite my bounds here to say, okay, we're evaluating if k equals 1, this is n. So infinity is equal to n, where k equals 1 is just our input index. Okay, so hopefully that makes sense. N minus 2, what is that? Well, that's going to be 3 over n minus 2 plus 3, that's going to be plus 1, minus 3 over, and this is n minus 2, so this is n minus 2 plus 4, that's n plus 2. Okay? For n minus 2, let's see what we get there. Or sorry, n minus 1. So this is going to be 3 over n minus 1 plus 3, that's n plus 2, minus, do the same thing here. This will be n plus 3. So notice our denominator is growing by 1 every time, so we can just cross out this and this. We know that at the nth term, this should cancel out too. What we need to do is say, okay, at the upper bounds of our infinity, what are we going to get? So let's also do n here. It's just going to be 3 over n plus 3 minus 3 over n plus 4. And that confirms that this gets canceled out. But we're left with this here. Notice, negative 3. So we're going to add that on here. Negative 3 over n plus 4. Notice that each term is canceling out. If we went to n minus 3, we'd notice that we'd see a common term here and we could cancel it out because it's going to be subtracted by a negative, and then we're adding this, okay? Because realistically, we're adding all these, right? But we're just listing them out like this to show that they cancel out. Lost my train of thought, but this would cancel, and we'd be left with this because we can't go n plus 1. There's no term past infinity. This is the infinite term here. So knowing that all these sums are going to cancel, reappear, cancel, reappear, cancel, reappear, we can say that the overall sum, S sub n, is equal to this term here. Okay? Hopefully that makes sense. Right? So all we have to do now is evaluate it at infinity. So let's take a limit as n approaches infinity for 3 over 4 minus 3 over n plus 4. was evaluate to? Well, 3 over 4, that's just 3 over 4. Notice that negative 3 over n plus 4, that's going to be 3 over infinity. That's going to cancel to 0. So this is minus 0, which just leaves us with this here. So not only does the series converge, it converges to a sum of 3 over 4. Alright, I hope you guys enjoyed this video. If you did, please drop a like, comment, and subscribe. I hope that you have a wonderful day.